Hello and welcome to the fifth Zoomcast of the ESE 461 course. On October 9th, Rana Mukerji presented the seminar titled Market Structure for a Decarbonized New York Electricity Market, in which she discussed the New York Independent System Operators, or NISO, progress in studying the needs of the grid to inform additional market design and operational enhancements. He described, with degrees from Rensselaer Polytechnic Institute, the Indian Institute of Technology, and Harvard Business School. Mukerji came to the US from India in 1981 at a time when, he quoted, power systems were very boring, or I should say he joked. And after gaining 40 years of experience working at GE, ABB, and currently as Senior Vice President of Market Structures for NISO, Mukerji now describes the energy industry as the most cutting edge, with growing numbers of young people who are committed to decarbonization, sustainability, and the ultimate survival of the planet. So before discussing decarbonization as the key to meeting New York's climate goals, I will pass it to Ahmed to discuss how the electricity industry has evolved over the years.
Thank you, Eva. The path that leads to today's enormous electric utility industry began in earnest in the 19th century with the scientific descriptions of electricity and magnetism by giants such as Hans Christian Ørsted and Henri-Marie Ampère and James Clerk Maxwell. The development of electromechanical conversion technologies such as the direct current dynamos developed in 1831, separately by Maxwell and Pixel of France, followed by Nikola Tesla work on alternating current generation and distribution along with the polyphase. Brushless alternating current induction motors in the 1880s made it possible to imagine using electricity as a viable and versatile new source of power. The first major electric power market developed around the need for illumination, although many others had worked on the concept of electrically heating a filament to create light. It was Thomas Alva Edison who in 1879 created the first workable incandescent lamp. Simultaneously, he launched the Edison Electric Light Company with the purpose of providing illumination, not just kilowatt hours. To do so, he provided not only the generation and transmission of electricity, but also the lamps themselves. In 1882, his company began distributing power primarily for lights, but also for electric motors from his Pearl Street station in Manhattan. This was to become the first investor-owned utility in the nation. Edison's system was based on direct current, which he preferred in part because it provided flicker-free light, but also because it enables easier speed control of DC motors. The downside of DC, however, was that in those days, it was very difficult to change voltage from one level to another, something that became simple to do in AC after the invention of the transformer in 1883. That flow in DC was critical since DC was less able to take advantage of the ability to reduce line losses by increasing the voltage of electricity as it goes onto transmission lines and then decreasing it back to safe levels at the customer's facility. Recall that line losses are proportional to the square of current, while the power delivered is a product of current and voltage. By doubling the voltage, for example, the same power can be delivered using half the current, which cuts I square R line losses by a factor of 4. Given DC's low voltage transmission constraint, Edison customers had to be located within just a mile or two of generating station, which meant that power stations were beginning to be located every few blocks around the city. Meanwhile, George Westinghouse recognized the advantage of AC for transmission, for transmitting power over greater distances and utilizing AC technologies developed by Tesla. launched the Westinghouse Electric Company in 1886. Within just a few years, Westinghouse was making significant inroads into Edison's electricity market. And a bizarre feud developed between these two industry giants. Rather than hedge its losses by developing a competing AC technology, Edison stuck with DC and launched a campaign to discredit AC by condemning its high voltage as a safety hazard. To make the point, Edison and his assistant Samuel Insull began demonstrating its lethality by coaxing animals, including dogs, cats, calves, and eventually even a horse, onto a metal plate wired to a 1000-volt AC generator, and then electrocuting them in front of the local press. Penrose, 1994. Edison and the other proponents of DC continued the campaign by promoting the idea that capital punishment by hanging was horrific and could be replaced by a new, more humane approach based on electrocution. The result was the development of the electric chair, which claimed its first victim in 1890 in Buffalo, New York, also home of the nation's first commercially successful AC transmission system. Another important player in the evolution of electric utility was Samuel Insull. Insull is credited with having developed the business side of utilities. It was his realization that the key to making money was to find ways to spread the high fixed costs of facilities over as many customers as possible. One way to do that was to aggressively market the advantage of electric power, especially for use during the daytime to complement what was then the dominant nighttime lighting load. In previous practice, separate generators were used for industrial facilities, street lighting, street cars, and residential loads. But Insull's idea was to integrate the loads so that he could use the same expensive generation and transmission equipment on a more continuous basis to satisfy them all. Since operating costs were minimal, amortizing high fixed costs over more kilowatt-hour sales results in lower prices, which creates more demand with controllable transmission line losses and attention to financing. Insull promoted rural electrification, further extending his customer base. With more customers, more evenly balanced loads, and modest transmission losses, it made sense to build a bigger power station to take advantage of economies of scale, which also contributed to decreasing electricity prices and increasing profits. Large centralized facilities with long transmission lines required a tremendous capital investment to raise such large sums. Insull introduced the idea of selling utility common stock to the public. Also, Insull recognized the inefficiencies associated with multiple power companies competing for the same customers, with each building its own power plants and stringing its own wires up and down the streets. The risk of the monopoly alternative, of course, was that without customer choice, utilities could charge whatever they could get away with. To counter that criticism, he helped establish the concept of regulated monopolies with established franchise territories and the prices controlled by public utility commissions, PUC. The era of regulation had begun. Thank you.
Thank you, Amen. The utility industry definitely has a very unique history. Alex, can you pick up where he left off and talk about the era of regulation and its impacts?
Sure thing, Ava. As Amen mentioned, utilities were heavily regulated beginning in the early 1900s. After the Second World War and up to the 1970s, we saw around 8% electric growth per year and the industry boomed. However, the market was disrupted in the 70s due to the 1970s oil crisis. This led to a series of further disruptions and eventually the deregulation in the 1980s and the 1990s. There were two major events that sparked the 1970s oil crisis: the Yom Kippur War of 1973 and the Iranian Revolution of 1979. Egypt and Syria attacked Israel, kicking off the Yom Kippur War. During this time, the Organization of Oil Exporting Countries, OPEC, controlled 56% of the world's oil. The U.S. provided arms to Israel, which angered the Arab nations in OPEC. They stopped selling oil to the U.S. and its allies, which created a large price hike and major supply chain distribution issues. The Iranian Revolution disrupted Iran's oil flow and took about 2.5 million barrels of oil off the market. So both of these disruptions combined, although they didn't completely knock out the whole world's oil supply, there were a lot of supply chain shocks, and this led to a lot of price hikes and overall disrupted the American economy. Now, in the 1970s, there were a lot of oil-based generation plants, and all these plants became too expensive to run due to the shortage of oil. So, at the time, electricity rates were determined by the regulator, and these rates were set when oil prices were normal, so they did not adequately reflect the increased cost of oil. So, as a result, a lot of these large central generation plants were no longer economically viable. They became what's known as stranded. So they were too expensive to run, but the customer was already obligated to pay for them. Now, around the same time, fracking technology had advanced and combined cycle plants came into play. So it was actually cheaper to construct and operate a combined cycle plant than it was to continue to run existing plants just because of the cheap availability of natural gas. So in addition to this, combined cycle plants could be placed anywhere with enough room to host them, so they could be located a lot closer to load centers. Now, federal and state regulations also required utilities to buy energy produced from combined cycle plants at a wholesale rate. So, if I open up a combined cycle plant, the utility has to buy the electricity that I'm generating off. And this was due to the shortage of oil, and they needed more electric power on the grid. And this contributed to the emergence of investor-owned generation. And all of these conditions together kind of led to the need for market reform. In the 90s, America began deregulating industries and allowing the market to create more efficient systems. As you open the door for competition, you drive efficiency. Efficiently structured markets promote the best technology, which creates space for innovation. Eventually, the deregulation trade made its way to the electricity and the NYSO. In one fell swoop, the energy market was formed. Day-ahead market rates, real-time markets, demand response charges, and congestion hedges all came into play. The deregulation of the energy industry transferred the risk from customers to the investor. Prior to this, the customer was stuck with the bill that the regulator allowed. Now, the investor was subject to the market rate that they were offering for the price of electricity. So, as energy generation became more efficient, financial payout transformed the grid. The NYSO implemented location-based pricing. So, areas that had higher demand valued electricity more. And this simple market signal incentivized developers to run high-powered transmission wires from upstate New York, which has plentiful hydroelectric power, to the city, where there was a premium on electricity due to the sheer demand and density of the electric needs. As we transition to a cleaner grid, we need more market signals like this to inspire tangible change, but centered around, carbon and things like that. When the markets were created, they incentivized keeping the lights on for the lowest cost. Now, we have a third issue to consider: carbon. Although the reliability and cost-focused market has led to more efficient plants that produce less carbon, there have been no signals that directly discourage carbon. Jess will elaborate a little bit more on this and how the markets are going to incentivize a cleaner grid going forward. But for now, back to you, Ava.
Thank you, Alex. It is definitely a large task at hand for New York to reach its aggressive climate goals. Jessica, can you tell us a bit more about the role of electrification and decarbonization?
Sure, Ava. Electrification is a huge, important aspect to decarbonization and arguably will be what ends up helping us meet our decarbonization goals. So there have been efforts that have already begun, but we have a long way to go before a significant impact is made. And one of the issues that needs to be addressed is a lack of incentives in the market for electrification or for less carbon emitting technologies like renewables. Developers are not financially incentivized to switch to more environmentally friendly technologies, and so a carbon cap and trade program or a carbon tax program could address this issue, but it would need to be implemented by regulatory agencies. And so ultimately, this would incentivize building renewables that could support the increased electrification for decarbonization. Renewable energy credits could also be used to offset the additional costs of renewables and make them more competitive in the energy market. But regardless, a method needs to be discovered or implemented to incentivize financially the reduction of carbon emissions through electrification. So as the public looks to use energy in an environmentally conscious way, the available generation on the grid will begin to dictate demand. So loads will change to meet the generation capacity online instead of generation changing to meet loads. So this hourly shifting of demand can be helped through the use of battery storage. Batteries could store power during the day and discharge it during peak load hours in the evening, which effectively would allow more demand to come online as far as electrification is concerned and still be able to meet it with renewable energy. However, the batteries don't necessarily solve the seasonal shifting issue that comes with renewables, where we see wind over-generating in the winter and solar over-generating compared to its nameplate capacity during the summer. So as electrification continues, the grid will shift to a potentially winter peaking system as heating systems are transitioned to electric heat. And so another concern there is the reliability of that system during these peaking seasons. So not that this is an issue, but it definitely highlights the need for long-term storage solutions that will be able to support electrification as the solution to our decarbonization needs. So along these lines, the biggest challenge is reliability. Resources like batteries near load centers should be compensated for their reliability, and system operators are working to accurately forecast intermittency on these renewables so that this reliability can be factored in appropriately. Demand is now much more unpredictable, and so solutions like rooftop solar and smaller storage systems that aid in electrification need to be considered in the grid where they previously weren't. So these are all some changes that need to occur for electrification to sit in the role that it needs to help with decarbonization. Operators need to predict the required energy reserves that are necessary to support these resources, and ultimately this will address the unreliability that's the largest concern right now. So if reliability can't be guaranteed, the deadline for these decarbonization goals will come and go if progress is lacking, because ultimately electrification is the biggest part of decarbonization as we shift to meet these goals.
Those are some great points that we heard in the seminar, especially the last point that you made about the importance of reliability, because at the end of the day, everyone expects that light to come on when you flip the switch. Jovi, I would love to hear about NYSO's current efforts to ensure that the grid remains stable and reliable.
Sure, Ava. The New York Independent System Operator has been proactive in spearheading initiatives to ensure the stability of the electrical grid. In light of evolving energy landscapes and the imperative shift towards sustainable energy sources, one of his groundbreaking endeavors is the integration of a carbon pricing mechanism. The rationale behind this is to internalize the external costs of carbon emissions, creating a direct economic signal for energy resources to account for these costs in their day-to-day operations. By doing so, the carbon pricing mechanisms aligns market outcomes more closely with New York's policy objectives of reducing greenhouse gas emissions. It incentivizes cleaner energy production, reducing reliance on carbon-intensive sources, and by extension, fostering a more resilient and sustainable power grid. Another pivotal measure taken by NYISO is the focus on net load forecast error. In an era where renewable energy, especially from variable sources like wind and solar, is being integrated into the grid at an unprecedented rate, forecasting becomes crucial. Variability in renewable generation can introduce discrepancies between anticipated and actual power loads. By concentrating on minimizing net load forecast error, NYISO is better equipped to handle sudden surges or drops in energy, ensuring that the grid remains stable even in the face of unforeseen changes in energy generation or consumption. Lastly, the concept of capacity marginal accreditation serves as another feather in NYISO's cap in its quest for grid stabilization. Ensuring that there is always sufficient capacity on the grid to meet peak demand is essential for any grid operator. However, the challenge is in recognizing and accrediting the genuine capacity margins that various energy sources bring to the table, especially with the diverse energy mix that New York's grid comprises. By focusing on a more precise and nuanced system of capacity marginal accreditation, NYISO ensures that every energy source, whether it's wind, solar, or traditional power plant, is recognized for its genuine capacity contributions, making the grid more resilient to demand fluctuations and ensuring uninterrupted power supply to end users.
Thank you, Joby. So overall, this seminar provided a very comprehensive overview of New York's electrification and decarbonization journey. It laid bare the challenges and complexities associated with transitioning to a greener energy landscape, and it emphasized the need for technological innovations, robust market structures, and a nuanced approach to policy formulation. One point that I especially loved during the seminar was when Mukerji was talking about the cost of decarbonization and paying for sustainable solutions. He noted that while cost is an important aspect, we really have to ask ourselves, what is the cost of not doing anything? Global warming is real, and we have to look at what is the best way to address this, not just looking at the total cost of things. So on behalf of the entire ESE 461 class, I want to thank Rana Mukerji for his insightful talk, and I thank you all for tuning in to the 5th installment of Zoomcast this semester. Until next time.